Hi guys, how are you after yesterday's party? So-so? Or okay. So turn your smartphone into Nintendo Wii-like controller with JavaScript and machine learning. Who knows JavaScript? 100%. Who has been playing with machine learning? Couple of you guys. So we are living in a world when we are using gestures from day one of our existence. We have been using native everyday gestures from saying hello to saying goodbye, just to greet with somebody or shake hands. But the advancement of technology allows us nowadays to use gestures to control environments. You can interact with the technology, you can play games, you can do a lot of cool stuff using your gestures and technology combined together. Who has played Nintendo Wii? So this is just the console, or not just, but it's a console that allows you to interact with the game with those kind of controllers that you hold in your hands and you move your hands to actually control the game. So it has built-in controllers inside, and the way you move your hands expresses your intention. You can play, let's say, baseball, you can play tennis, and the game would actually be able to understand what you do. So my name is Bartosz Pietrucha, and today I will tell you how to do this with your smartphone. You can follow me on Twitter, and also you can visit my website when you can find information about trainings which I provide in Angular. So we will start with the demo. So here's the website, and I want you to look at me for a second. I'm holding my smartphone, and take a look. If I do this, the arrow will show the direction in which I move, right? So for some reason, some magic way, the phone understands in which direction I move my hand. I can control, and this is the very simple example, but imagine what happens here. I'm holding my smartphone, which is running the web application, and I'm able to control what happens around me in the web app. So basically, the phone has built-in model that understands the movements because I have taught the model what it means to move your smartphone left, right, up, or down. These are the basic examples that we'll learn how to implement with the web application. Are you excited? Yeah. You're excited. I see it. Okay, guys, so we have seen the demo in which we had running web application, my interaction with the phone, and under the hood some JavaScript and machine learning. How it works. Here's how. Let's start from the definition of machine learning. There is a gentleman called Tom Mitchell who has contributed to machine learning a lot. And he has come with this definition. Machine learning. A computer program is set to learn from experience, E, with respect to some class of tasks, T, and the performance measure, P, if its performance at task in T as measured by P improves. So the more we train the model, the more we train the machine, it gets better and better in solving our tasks. So what kind of problems do we solve with machine learning? Let's start with the first group of problems. It is combined together into so-called supervised learning. In supervised learning, we have basically two kinds of problems: classification and regression. Our example with gestures was the example of classification. This problem, given the examples and the labels, as you see here, okay, this is, I thought that there is the laser, but it's not here. So The classification problem, we have the red star and the black triangle. So these are some objects. So we are showing the examples in some space where we describe those objects. And in this case, this line is showing us some kind of separation between those classes. And then if there is a new object that we don't know what is the class of, and depending on which side of this line it falls in, we would classify it either class star or the class triangle. So this is the problem of classification. We are showing some examples, and based on those examples, the model would know later if there's an unknown example, as if it was in my example, I was doing some gesture, I was not telling the program what it is, and for some reason it was able to understand or classify it. So classification problem is finding an answer in discrete space, comparing to regression. In regression, the answer lies in continuous space. So in this example, imagine that the horizontal line represents the data, let's say height of father. And then we measure those heights, and on vertical line we have height of the child. And we find a pattern. And then based on that pattern, we would be able to predict the height of the son given the height of the father. So we found some pattern and we generalized over that. So this is the regression problem. We are finding the pattern that allows us to answer the question in continuous space, not in discrete space as if it was classification. Other group in machine learning is unsupervised learning. In this case, we also deal with the data. But clustering problem may be similar to classification, but in this case, we don't know the labels. We are not supervising the training of our model. We would be given the data. The program is supposed to find the clusters by its own. So similar objects, right? So in this case, there are two clusters. Those objects are somehow similar, but the program does not know if it's a triangle or the star and so on. So it tries to guess, based on the similarities in the data, what are different clusters. And dimensionality reduction also, we are not supervising our program or our machine. In this case, the problem that we solve is to try to describe the data in lower dimensions. Imagine we have the vector of 10 or 100 dimensions. How would we plot it in the graph? There's no way to do this in an easy way. So what we would like to do is to find a space in which we would be able to describe this data, not losing its characteristics. So in this case, what happens here, two-dimensional data is mapped or projected into one dimension. The same may happen if we have more dimensions to be able to describe the same data. So we are reducing the number of features needed to describe the same data, trying not to lose its characteristics. Who understands this? Okay, who does not understand it? Okay. Imagine that those points here are described with two numbers. Let's say the first is like 1 and 2, like x and y, plotted in two-dimensional space. And here, we would like to reduce the number of features, only use one number, like x, to describe it in only one-dimensional line. So we projected it, but the characteristics, like, it's not lost at all. It somehow represents the same data, but only with one number. Does it sound more or less logical? Cool. Let's go further. So we know 4 classes of problems that machine learning can solve. Another idea is to know the difference between different kinds of models. We can have parametric model and non-parametric model. In the first case, the task that we would like to solve is to find the parameters, in this case A and B. So we are making some assumption that our data would be described by this equation. So we assume that this is the line, that our data form a line. This is just an assumption, right? So here, our goal is to find A and B, and the values of these parameters would fully describe the model. In non-parametric case, there is no assumption over the model. We don't have any assumption about the function. So in the first case, we can presume that it's going to be faster, but maybe a little bit less reliable. In the second case, we would be more robust, but we will need more computing power to find the model because there is no formula known as in the first example. So this case, this function may be totally very, let's say, there would be even no mathematical formula. There would be some recipe to find the value of y. There would be no function in so-called mathematical description meaning, right? We will not be able to write a formula like this. We will then later understand how it works. So example of non-parametric model. KNN classifier, our main actor for today's show. It needs arguments, which are distance function and the value of k. So imagine we have, again, some two-dimensional space. We have stars and triangles. And there is yet another guest in this space, the unknown guy. So what this model or classifier would do to try to guess who is this guy? So assuming the value k equals 4, we would take 4 nearest neighbors, as you see in these lines, given some distance function that we know how to calculate the distance between those guys. And there is 75% probability of red star, because 3 neighbors out of 4 are stars. So having them described in this way, classifier would know, or would predict that it's going to be a star. It's a very simple model, yet very powerful. And again, there is no mathematical formula saying x equals a plus b plus c plus d. We have some algorithm to execute to find the prediction. This is k nearest neighbor classifier. We'll use it to classify our gestures. What is a distance function? Imagine that we are in 3-dimensional space. So what would be the distance between me and this speaker? We would need to calculate, given the characteristic of 3-dimensional world we live in. This would be called Euclidean distance. And this formula would give me the distance between me and this speaker. But also I'm a speaker, and this is a speaker also, right? That's weird. So there would be also another formulas, like Chebyshev distance. I don't know if this gentleman comes from Russia, but it has like this kind of surname that maybe he's somewhere from here. So Mr. Chebyshev came up with this equation. The distance would be just the maximum of all vector dimensions. So imagine we have 2-dimensional space, and we take only the maximum from x and y, and would be also a fair representation of the distance between those 2 points. Okay, the next question. How to apply all those crazy stuff to gesture recognition task? First of all, what we need? We need a smartphone. And most of your smartphones has accelerometer built in. What is accelerometer? Accelerometer is a small device that will show us the acceleration we are actually applying to our smartphone. As we would move this device, and if I move it up, there will be some signal generated, x, y, and z, representing this movement. This is a very simple device. how to build or how it is built inside of your smartphone. It's just a spring mass and some material that has very important characteristic. So if we see in this animation, as we move this device up, the mass that is attached to the spring, according to the laws of physics, would have the force of inertia that would pull down and press on the material. And the force applied to this material would change the potential that this voltage meter would show. And then, based on that value, we can calculate the acceleration in the given direction. And these are very small devices built in your smartphone, which we can read from. How can we plot this data? So, as we hold this smartphone or this device, over time it will generate some signal, right? So, if I stand still and don't move, there would be nothing interesting on this plot. But if I do something interesting, you would see some spikes, and it would represent some kind of movement. So we would like to pull this part of the signal, apply it to classifier, and predict the value of the classifier model prediction. But how do we know when this gesture starts and ends, right? Because we have some continuous signal. We need to have some strategy to understand or to know which part of the signal would be something interesting for us. We can do some kind of segmentation. And a very simple approach would be based on some kind of threshold. So if the value of the signal would be strong enough, let's call it some threshold, we would assume that it is something interesting. Because if I just do very little movement, maybe nothing interesting. But if I do strong enough movement, the signal would be interesting for us. So as you see in the example, if we are above a given threshold, we would pin this particular point as a start of the gesture. And if we are falling down below this threshold, we would say, okay, we are done, we know the segment, right? And also we can have some, let's say, cache at the beginning and at the end of the signal, and this would represent our segment. Yes or no? Cool. I know it's very early and probably you had very interesting after party. Me too. But that's fun. Okay, what value should we apply? I have done some research and found out that the values around 60 and 70 meters per second squared, because we represent acceleration with the units meters per second squared. And the value of 16, 17 tends to present the best performance, because I asked a couple of people, could you hold the smartphone and make some gestures? And assuming that there were, let's say, 10 gestures, and the number of correctly segmented gestures was when we applied about this kind of value. Why? Because if the threshold was too low, it was catching too many gestures, right? Because if the value was very sensitive, very small movement would be assumed to be a gesture. And if the value was too high, if people were doing like slightly moving gestures, and the threshold assumed that this has to be this value, it was not catching enough gestures. So this was kind of optimum. Again, our KNN, K nearest neighbors classifier, comes on the show. So imagine that we are able to describe those gestures somehow. We have our segments. Assuming also we know how to calculate the distance between them, we would be able to apply our classifier. So we just calculate the distances and find the ones, the only one that would be the closest to our unknown example. Yet another question, how to calculate the distance between gestures. These are the signals, right? So this is just a, let's say, array of points. And we need to know how to calculate how far from each other they are according to our classifier. So there is the very interesting algorithm called dynamic time warping by Mr. Miller and Maynard in Springer 2007. They came up with the algorithm that having two sequences, we can have a value representing their similarity. So let's take a look. This is the pseudocode of the implementation of dynamic time warping. It takes two arrays, some cost function, and it will give you the value. So you can implement it on your own, like for if return, or you can be as hacky as I was. As simple as that. npm install, and you have fair implementation of the algorithm that we need to solve the problem. So how does this look like? Let's record a couple of gestures, like left, up, right, and down. They would look maybe, those two kinds of gestures, like left and right, they may look like that in the charts presented on the bottom of the slide. On the middle on the slide, we have a table with the values. And if we see that left one and left one, which is exactly the same gestures, the distance, according to this algorithm, is 0, because they are the same. But if we compare different left instance, the value is above 0. And if we compare instance of the right, the value is even higher. So the distance between them is higher. They are not as similar as different examples. So we have a fair representation of the distance between those gestures in this feature space, right? This is what we need. We need a number that would represent the similarity of those sequences. Do we have all we need? Let's see. So the last, maybe one of the last pieces that we need is how to get those points in the web application. There is an event in the browser which is called device motion. This is the Angular implementation, but you can listen to this event device motion just applying a event listener. You would have an event, some function, and then we would have an object called the object would have a property. The property acceleration would have x, y, and z. And then we take these values, wrap them into the object, and apply some logic to this. This would be generated very, very often. I don't know exact frequency, but if you would plot these values, it would be very, very lot of data points. And this would form this kind of charts, right? So we just need to listen. So having the website, it's just as we can just run a simple website, just a website in our smartphone. Start to listen to this event, and magic start happen, right? We have the device motion data in our web application. What is next? How to implement segmentation. For my case, I have wrote so-called marker functions that I was applying over and over these data points. As you see, this handle point was trying to guess in which stage of the signal we are. If it's the beginning of the gesture, if it's the middle of the gesture, if it's the end of the gesture, if it's no gesture at all, right? So I was asking every single point, hey, is the gesture start? Is in the middle of the gesture? And I was just comparing some magnitude, some flags, and then I was able to extract the particular segment, right? So every call to handle point was checking what could be this part of the segment. If it's the middle of its end, we need to find out. Okay, guys. So we have learned how to use web application data points from device motion, compare them with the examples. Because the important, or maybe the most important, for this problem is to show the examples, to create those data points, right? So imagine that you would like to teach the smartphone to play tennis. What would you do? You would show the examples, right? This is the forehand, this is the backhand, right? I'm showing you how to play tennis. Or maybe you would like to play archery, like, and you show the examples, what it means to do the gesture. Let's see again here, or maybe I would look here. You form your feature space, like this would be the examples. Then you find some function. You can use the one that I was using in this example to calculate the distance. You apply KNN classifier and you would turn your smartphone into a game controller. That's all the magic that actually I have shown you. So let's recap what we have learned again about machine learning. Supervised learning recap. Classification and regression. Who remembers in what feature domain or what domain is the target value? Continuous or discrete? Discrete. Why? Because the answer is not a number in like continuous space, right? And regression. What problem can we solve with regression? Who remember? I mean, we know that it's a continuous, but can we come up with some example? Let's think about what we can predict. Exactly. The temperature, the price of the house. So we gather the data, right? We show the examples of the known instances. For example, given the factor of, let's say, number of clouds today and humidity, we know that the temperature is this. And we gather those data and build a model. So what algorithms can be used to solve this kind of problems? A very simple one is linear classifier. This would be just the linear combination, like AX1, BX2. So we need to find parameters to apply linear combination. Linear combination is just like as you would have linear function, AX plus B, Y plus D, and then so we apply some factors, we multiply those features and form some linear combination. So look at this example. Again, we have some classes, red and black and white, and we strive to find a function that would be a fair separation. We will call it discrimination line. And as you see, the red one looks like the most fitted example of our classifier. The green one, totally not good, because it classifies the white ones as if it classifies the white examples, right, as if they were black ones, right? Because if I would place another one on the left side of this green line, it will think that it is probably the black one. But if I would be very close to the white one, it should be classified as a white one, right? Because the examples are showing from the data different pattern. So the one which is blue also may work, because according to the data, it is 100% accurate. All the examples would be classified correctly, right? So how this classifier can be trained? It can be trained with the optimization algorithm. What is optimization algorithm? According to some input, we would like to find for which arguments the value would be minimum. So we have the difference. We need to find a formula. These are just x and y values represented with two-dimensional vector. So we would try to find the difference between the prediction and the real value and minimize it. What I mean by minimize it? Find the the parameters of the linear combination that would give you the minimum possible value for all the examples. And then this optimization algorithm would find the parameters for this line that would be the best match for this kind of data, because this is the most important. The data are the main players who dictate the model. We need to have data which are representing the phenomenon that we would like to generalize upon to find the model. Another example of classification, maybe some classification tree. In this case, you see the example of Titanic survival. Based on the data, they have built the model that, having answered you a couple of questions, predicts your probability of survival. So if you are a male, if you were not a male, you had 73, the first number, 73% probability of survival on Titanic. If you were a male, there is the next question. The other factor that played a very important role for your life. So if you were younger than 9.5 years, or let's start from the different leaf. If you were older than 9.5, you probably died. If you were older than that, the other question is, no, if you are younger, the answer for this leaf would be, are you older than 9.5? No, and then there is this factor SIBS. It's the number of spouses and siblings. The number of spouses and, sorry, not and, but or siblings aboard. So if you have more than 2.5, that are chances that you probably survived. So again, based on the data that actually were true and realistic from this actual phenomenon or actual historical facts, they built a model of chances based on classification tree. Yet another way of building classification model. Okay, let's go back to unsupervised learning. We didn't have any example in this demo, but I will try to give you a little bit more insight what you can achieve when these tasks that machine learning can solve. So we have clustering that tries to find similar groups of data. We have also very nice, yet powerful and simple algorithm which is called k-means clustering. Let's see that we have a bunch of gray points, and we say, okay, I would like to group those points in 3 clusters. There are 4 very simple steps for this algorithm. I will explain you now. So we know that the k is 3. We say, I would like to find k in automatic manner, totally automatic, because imagine that you would have a lot of different points in a lot of different aspects describing a lot of different things, right? And you want to group them together to find similar objects. So we would throw random 3 points, and then according again to some distance function, we would calculate for each point the center, which is the closest one. So the red point, then we look for 3 different centers of the clusters, and it seems that the red one is the closest one, right? For green one, you see that the points that are green found the green point to be the closest one to it, right? So we form the initial clusters because those was generated randomly. In the third step, we know the initial, let's say, clusters, and then we would move the center of the cluster to the geometric center of all the points or the objects in that cluster. So you see that the red one is only 1. So the center, geometric center of 1 point is exactly this point. For the green, the center of this geometric, let's say, it's a geometric mean, so like a geometric center. There is a formula for calculating the geometric center of the points. So we move the center to this point, And we have yet another proposition of clustering. You see it on the 4th slide. And then we move it again. We repeat the number 2 step and the number 3 step as long as the position of the centers change. If we converge to the point, this is called convergence. Like we are trying to converge this model to the point where those centers does not change anymore. So we found the best representation of clustering for this particular data points. So imagine that you throw, I don't know, anybody can come up with some idea of clustering of data? I will give you a couple of seconds. What do you think? What can we cluster? Okay, we have an answer. What can we cluster? Mm-hmm. And what those cluster would can okay, the severity of crime maybe. Like we have, let's say, yeah, yeah, I know what you mean. So we would like to find a regions on the map that, according to those points, represent some, let's say, crime factor, right? Or what is the region? We have the data over the map, and we would like to maybe find the places where is the highest chance of, let's say, flu epidemic, right? So we have the data, and we apply some algorithms to try to know more what is happening in the real world based on our analysis of data, right? Oh, we are on good timing. And the next next algorithm is called PCA, Principal Component Analysis. And this will help us to present high-dimensional data in lower dimensional space. Look at this. We have two-dimensional points. And there are some interesting characteristics also in this shape. We found so-called principal components that shows us the directions in which this data represents the most I always fail. Variability. Yeah, thank you, man. Variability. Exactly. So you see that there are two dimensions or two directions in which we find the most this thing. That thing starting on V. And we can again try to take the one which is the longest and project it. In this case, we'll project two-dimensional space into one-dimensional space to present it on only one direction, on one dimensional space, which would be a simple line. So we'll remove one dimension for the and get only one dimension, like from 2 dimensions with only 1 dimension. But this can be applied to 100 dimensions, and then we would be able to visualize very highly dimensional data in some lower dimensional space to make it like a graph. Because how many dimensions we can plot? 3? If we use colors, maybe 4, right? Because you can draw like 3-dimensional chart. You can add colors to it to represent yet another dimension, but it will be hard to visualize 5 dimensions, right? So we can reduce the number of those dimensions. The last one, is artificial neural network that can solve basically all of those problems. Supervised learning, unsupervised learning. If you use proper neural network, you can solve basically all of those problems. We have a couple of minutes for the questions. So what is the conclusion? What conclusion can you take out from this? If you don't know, I will tell you. Machine learning is easy. We have learned the fundamentals, right? We know what problems can we solve. We have built a model. We have understand the most important tasks that we can solve, right? Do you need PhD in mathematics to understand what I just said? Do you need PhD in statistics to understand what I just said? No. Thank you. Just catch up on Twitter. And I guess this is the time for questions, right? If not,
of course.
Thank you very much.
Thank you, Bartosz. Do you have any questions? No questions. Oh, one question. We have one question.
Thank you for your talk. You told that when you're calculating the distances between the points, between your movements, you should have some start data, some start set. But you didn't show us the start data for your app. Maybe you can tell how many data did you have and how long did it take you to make preparations for this demo? Thank you.
Okay, let me check. I don't remember how many examples did I have, but this is my data set. So
Pretty big.
and because what happens if we try to format it? Okay. So you see this is the gesture left, and it has a lot of data points, and yet another gesture left. These are the sequences of those points, right, that I recorded. I don't remember how many of them they are there here, but I can scroll over.
Okay, I understood. Thank you.
And this is the set that I used for the sake of this particular example. But as I said, you can try to come up with your own ideas, right? The demo was showing you those kind of gestures, but your imagination is your limit, right?
Yes. And one more question.
Sure.
You said that move device event would fire very often.
Yes.
A lot of times in a second. And every time we should calculate the distances between all these points.
Not really. What you need to do is take a look what we have here in this data set. We have the label left, and it has all those points. You see this point, and this is my sequence. And then I would need to calculate the distance between this gentleman here and the next one. So let's find this one. This is, again, another example of the sequence of points that I set to the model that I know it is the gesture to the left. So then I take all these points and have the sequence. Remember, let's go back here maybe. So we had this algorithm. And you see that it takes a series on an input, the sequence. So we were calculating the differences between the sequences, not the points.
Understood, but every time you add a new sequence in your data set, yes?
You actually are pointing to very good aspect. I told you that we have non-parametric models which are basically more computationally expensive. So the more data we have in the training set, the more expensive it gets to calculate.
Yes, and every time you have your set is growing bigger and bigger,
it will take longer.
Your event will fire very often. Maybe could you debounce it somehow? And maybe you should make rotation of your data.
Maybe. I mean, this may be.
It's up to us, yes?
I mean, yeah, we can, because imagine that instead of 10 examples, you have million examples. This algorithm would be much slower, right? So, as I told you, non-parametric models may be better performing in the case of accuracy and robustness, but they may be, let's say, more expensive. And then we need to find some another maybe approaches that will make it faster, make it more efficient. This is just the beginning, right? Because this is what engineers do, right? And solve real-world problems to find the solutions to this kind of problems.
Okay, thank you for your answers.
Sure, you're welcome.
Any questions? Oh, have one.
Another idea maybe also, hey, I would like to also extend your question. There is also so-called feature extraction. Sometimes when we have too much features that we don't, for example, want to calculate, we will apply some kind of algorithms which are so-called feature extraction. So we will take only the points or maybe the features from all points. This doesn't matter in this case, but imagine you have, let's say, a picture of the face, and you would apply classification of different faces. Maybe this is how old is the person, or who is this person. So the image would have a lot of pixels, and maybe applying your feature extraction, you would only want to take the points which are significant. Maybe where is the eye, where is the mouth, where is the ear, where is the cheek. So you would apply some algorithm at the first phase to extract the points which have significance, right? So maybe your eyes are only important, maybe your nose, ears, and cheeks. So you would extract particular features, not to use whole picture, because every single small pixel would maybe not a good choice for you.
One more question. Do you open your source code for the demo with arrows?
I plan to do this in the nearest future.
Thanks.
I maybe, yeah, for you to stay. If I ever open source it, my Twitter handle is the place to look for it.
Any questions? Actually, I have one. Do you plan to make your own game in browser?
Maybe. Maybe we can build some game and play. But just out of the blue, I remember there is some project that allows you to play some games, but this is not using probably any sophisticated machine learning models, but it can use acceleration data to simulate the behavior of the steering wheel. So you take your smartphone and it generates all those points, and then you transform, like the tilt, and then you calculate the tilt of your phone, and then it can actually play a role as if it was a steering wheel, right? So as far as I remember, there are some kind of games that make use of this tilt to make this way of controlling what happens in the game.